Now that we are getting more involved in understanding how the packets arrive at the input queue and how these are processed, it gets important now to understand what happens when the queue is already filled up. So, for the packets which are occupying the queue, what is going to be the impact for the newly arriving packet? How will the newly arriving packet look at the queue? Is it going to look at it as an empty queue, or it is going to look at it as an already filled up queue and is going to affect the arrival process as such? We are going to look at the arrival occupancy distribution. That is, the distribution which results with the occupancy and the arrival subsequently. First, we'll understand why do we need to understand the arrival occupancy distribution for a system that is continuously evolving. What are the non-typical and typical arrivals? And then we'd look at the distribution. The reference is Bertsicus and Gallagher. First of all, let's agree on something. That is, a queue or a router is expected to be continuously under change. The packets would enter the system and leave the system. So the system would have a dynamism, and this dynamism would reflect a continuous change in the number of packets arriving and packets leaving. But what comes has to go. Therefore, the effective number of packets which arrive have to equate to the number of packets which depart. But there may be some instances when the arrival of packets is not following the typical or the average, rather it is an anomaly. Say it's an outlier. So it means such a packet would arrive at above average delay. So that could be represented as non-typical arrival. It could be represented through a simple mathematical formulation, that is A sub n, that's arrival of nth packet, that happens just after time instance t, where t approaches infinity. It means the arrival is infinitesimally small, is based on infinitesimally small interval. It is happening just right after the previous arrival. Is this going to affect the way we have looked at our system as a Poisson and exponential system? For that, let's look at a typical system. In a typical system arrival, the arrivals are going to follow Poisson distribution. That means the arrivals are going to be such they are going to respect the mathematical formulation or the graph that we saw earlier. Equating the two becomes very easy now, because no matter how atypical or non-typical the arrival may be, it still is going to be in disjoint time intervals and independent. Therefore, it still is a Poisson distribution. So all the incoming packets are still going to find an already occupied, unoccupied, or partially occupied system as a typical Poisson process that is going to service as an exponential system. The future arrivals are going to be independent of the current number of packets or customers in the system.